Okay, for the 100th time, this is the tutorial for the Matlab Markowitz Sufficient Frontier script that I've just uploaded to Facebook, and let's just get started. I've done that shit like 5 times now and I've fucked it up every single time. Alright, one more time. You just gonna open Matlab 2012 or 2013, doesn't matter. I've created a folder called Markowitz all. You don't have to do that, just drag and drop the markowitz.m script, the one that I've uploaded to Facebook, in here. Then what you want to do is you want to prepare your Excel data, so your data stream data, in a way that MATLAB can easily understand it. This is done by saving all your stuff as a so-called CSV file. CSV stands for comma separated value document, or actually just comma separated values. In my special case, I have 4 different periods. If you just have one, then we'll just have one sheet. The point with CSV files is every CSV file can just be one active sheet. So all that stuff that I have going on down here, each of them is its own CSV file, as you can see. Just make sure you have one line of names and then all your returns. These are already the daily log returns. I've already calculated that, but you could do that all in MATLAB as well, but not with my script because I was too lazy to do that. So what you want to do is you want to save them as format comma separated values file, CSV. On Windows it's slightly different name, but you'll get it. It's not that complicated. There's 3 different CSV files and just one makes sense. Choose the one that says comma separated something something. Save it as whatever, click the save button, and then yes, yes, always yes, no matter what it asks, just say yes. If you have more than one file like me, you go to the next one, save it, change the name up here. Alright. When you've done that, you go back to MATLAB, you click the import button, which is in 2012 is right here, and 2013 is up here. So click import data, navigate to the path where you've just stored all the CSV files, import CSV file, boom, boom, boom. Make sure that it says column delimiters, comma, because we just created a comma separated value file for that purpose. Variable names row is 1 because we have the first row in the data set that we have saved are the names, or at least in my file it's names. If you have 2, then you would change that to 2. You want to save that as a matrix. I think 2012 doesn't even give you all those features. It will just say save and then you'll just save it. The only important thing is if you have hashtag value inputs here, make sure they are being replaced with NaN. Click the save button and voila, we have a file called P1. If it's not called P1 or whatever, just click the rename button and rename it. It's 782 times 9 observations. 9 variables over 782 observations. Double is the number type. That means it has, decimals. That's enough. Alright, what we have to do now is we have to calculate the average return. In Excel you would now calculate your descriptive statistics, and in MATLAB, because I was too lazy to code that up properly, we have to do that by hand. That is just 2 lines and we're done. Alright, so we want a variable called P1 ret. This is the return of the sample. If you call it differently, you want to call it different again, equals mean of P1. If you do it, you'll get a column vector, row vector, but we want a column vector, so we just say P1 ret equals P1 ret transpose. See that? Now we have a column vector. Alright, these are the returns. Next, what we need is we need our covariance matrix. The point in Excel is Excel will not give you the correct covariance matrix because it's not adjusting for the estimation bias. MATLAB will do that. What I mean by that is your results in Excel will, number 1, be different, number 2, be wrong. Because Excel does not give you an unbiased estimate of the covariance. MATLAB does. So we store that in a variable called P1 cov. Something just happened. Am I still recording? I'm not sure. Yes, I'm still recording. Great. P1 cov equals covariance of P1. Boom, here's your covariance matrix. Alright, what do we need next? To get a really nice efficient frontier graph, what we want to do next, you will see why we're doing that right now, you want to calculate, I did that in Excel because it's just easier and faster. You want to calculate the, or you want to take those returns that you already got here, those, boom, and copy them to Excel. And then you want to annualize them. See, these are the returns. I've just copied them from here to here, and you want to annualize them. You annualize them with this formula. All right. What it does is it's annualizing them, and this is the number of days in a year. Annualizing means make something that is daily, monthly, weekly, whatever. You know, calculate that in terms of years. I have 260.67 days in a year. Given the fact that I have 782 observations divided by 3, you will get that result, roughly. And if you have 250 days in a year, change that to 250. If you have 360 days in a year, change it to 360. Not very complicated. Alright, this will give you the annualized data. Just, you know, copy paste that. Copy paste them, boom, boom. And while you're with your mouse over here, input that and call it P1 red n for annualized. Column vectors 1 n import. Great. Next thing we need is we need the annualized standard deviations of the respective shares. So what we want to do is we want to calculate the standard deviation, sample standard deviation, which is important, of each of the variables. This is all the observations. Boom, we get a value. What I've done next is I have calculated, or I've what I've done next is I have annualized the data, and the variance or standard deviation is, the standard deviation is annualized by multiplying it with the square root of time. See that? Boom. Copy it, transpose it, get those values, take them, copy them, input, call it, what do I call it? P1 std n. This naming convention is actually important. Store them. Okay, basically now you have everything you need for the code to work. I'll just quickly go through the code with you to explain how it actually works. Alright. Surprise! There's the code. Because you might actually have to adjust it. You do not want to change anything up here. This is important. Don't change anything. The code will automatically understand how many variables you have in your or how many variables you have in your observations, so how many stocks you have included. This model does not allow short selling, but you could change that in here, but this would take me too long. I don't want to explain that. What it does next is we enter a for loop. The for loop will go through 100,000 iterations, which is quite a lot. So every single time you change the target return in Excel's solver, you'll get one observation, and this thing does that 100,000 times. So you see there's, you know, it's a lot better. This is the actual optimization line. Quadproc is the optimization function. Here we are calculating the portfolio mean for the set target return. Just, you know, normal formula, weights times the returns, and then sum it up. Portfolio standard deviation, I call it PVAR because I'm an idiot, but it's actually the portfolio standard deviation. The annualized values, again, if you if you don't have 260.67 days, which you definitely do not have, change to the amount of observations you have, divide them by the number of years you have, and you'll get your days in a year. PVAR annualized is the annualized risk of the portfolio in terms of standard deviation, and P sharp is the annualized Sharpe ratio. Output is where all of our output will be stored, we are not accessing that. This is just for, you know, for the algorithm to work with. But it saves, so that you understand it, it saves the daily mean, the daily standard deviation, the yearly standard deviation, the daily standard, it saves the daily mean, the annualized mean, the daily standard deviation, the annualized standard deviation, and the Sharpe ratio for the annualized values. And down here you might have to adjust that if you have more than 9 variables, and I think you have 15 or 25 or something like that, you want to add, you know, whatever number of lines you need. So the next line would be output 16, I equals x 10, 1, and so on. If you want to do that in another for loop and you're smart enough to do that, go ahead. I was just too lazy. We're going to reset the values here, and this is all unimportant for you. Down here is the next important bit. This part finds the optimal portfolio. So we're looking for the maximum annualized Sharpe ratio, which basically says look for the maximum value in row 5, which is where the Sharpe ratio is stored. Then return the column and the row in output. So maybe it's in row 5, but column 470 or 12,000, because we're having 100,000 observations in there. So there's no point in manually looking that up. This is impossible. It'll find that value, and then it'll find all the daily return, daily standard deviation, yearly return, yearly standard deviation that correspond to that value, and stores all of that in the optimal allocation column vector. You will actually see this column vector. This will be your visual representation. You will get that on the screen in a second. Down here, you might want to add some more, you know, output fields here, because these are the portfolio weights. If you have more than 9 shares, it's very likely that you will need additional rows here. So next line will be output 16, col. All right, down here you're plotting the efficient frontier. Output row 4 is the annualized standard deviation, and output row 2 is the annualized portfolio mean. Title is the title of your plot. You can change that to whatever you like. X label, easy. Y label, easy. Down here, what it does is it finds the optimal allocation, so the value with the highest Sharpe ratio, and will mark it with a capitalized O in the graph. Then it will print the graph, will actually create a file for you, a PNG file, which is a graphic file, and call it efficient frontier. You can change that name to whatever you like, and then it will. This is where everything comes together. Then what it also plots on that efficient frontier is the returns and the risk of the individual companies. That's why we had to annualize the return and the standard deviation before. This just says that there's axes. The tick and talk in the beginning and end just measure how much time the algorithm required to do all the operations. So let's click the run button. Boom, 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 boom. It runs through, and it's done. Boom. Alright, the efficient frontier doesn't look as nice as it did in the other version, so what we do is we're going to manipulate that a little bit. But before, see below here, it took 8.5 seconds to calculate everything. Daily return, daily standard deviation, annualized return, annualized standard deviation, annualized Sharpe ratio, and as you can see in this portfolio combination, the investor would only invest in 3 companies. Stock number 1, 3, and what's that? 9, 8, 7. Which does make a lot of sense because all the other ones have negative returns, and you would not invest in something with a negative return. See 1, 2, and 3 up here. Alright, let's just say we do not like the colors. We want to have that a little bit cooler. You could do that all in with code, but I was number 1, I'm too lazy. Number 2, I have no idea how to do that. And number 3, it's just, easier to do it that way. So what you want to do is you want to go to Edit and click on Figure Properties. This cool feature will open and will allow you to manipulate almost everything. If you don't like that gray background, just change it here. Choose another background. I'm just going to stick with that. And then you can click on